Good morning everyone, I am Qingyong Hu, a PhD candidate at the Department of Computer Science at University of Oxford, supervised by Professor Nikki Trigoni and Andrew Markham. It is my great honor today to have this opportunity to share my research with you. Recently, point cloud learning has attracted increasing attention due to its wide applications in many areas, such as autonomous driving, AR, VR, remote sensing, and also robotics. As a widely used representation for 3D objects, point cloud has several appealing properties compared with other 3D representations, including 3D mesh, voxel grids, and multi-view images. First, it is the closest representation to the raw sensory data, and it preserves the original geometric information without any discretization. It is also flexible and compact, similar to 3D mesh, thereby suitable to represent large-scale 3D scenes. Finally, compared with 2D images, it is also highly robust to light and weather conditions. However, point cloud data has its own challenges. First, it is orderless and irregular. Different from 2D regular grids, given points irregularly sampled from local neighborhood, it is infeasible to directly apply standard CNNs on this kind of unstructured data. As shown in this figure, if we directly applied a regular fixed-order kernel on this data, for most cases, F2 is always equal to F3, but in fact, they represent different patterns. On the other hand, F3 usually not equal to F4 because of the different orders, but indeed they represent the same pattern. This is the reason why we cannot directly apply standard convolution on unstructured point clouds. In addition, point cloud is also non-uniform. The density of point clouds is usually varied according to the distance to the depth sensor. Furthermore, the raw point clouds acquired by depth sensors are usually large-scale and immense. For example, the data from Semantic3D usually contains more than 10 million points and over 100 meters space. Here is the roadmap of point cloud processing. Early methods usually build upon hand-crafted local descriptors. It can be roughly divided into histogram-based methods, signature-based methods, and transform-based methods. Recently, deep learning on point clouds has become more and more popular, with numerous methods being proposed to address different problems in this area. Existing learning-based methods can be divided into projection-based and point-based methods. For more details, please refer to our survey paper. Here, we mainly focus on learning-based methods. In particular, we will investigate the point-based segmentation methods. First, I will give a brief introduction to projection-based methods. They usually first project an unstructured point cloud into an intermediate regular representation, for example, multi-view images, spherical images, voxel grids, and sparse lattice. They then leverage the well-established 2D or 3D convolution on this intermediate representation. Finally, the pixel-wise or voxel-wise semantic labels are projected back to the raw point clouds. The problem of these methods is that they usually introduce the information loss. Different from projection-based methods, point-based methods directly operate on raw point clouds without any voxelization or projection. These methods do not introduce explicit information loss and become increasingly popular. It can be roughly classified into point-wise MLP methods, PointConvolution methods, RNN-based methods, and graph-based methods. Here I will introduce several milestone works in this area. First, PointNet is the pioneering work to directly process unstructured point clouds. It learns per point features using shared MLPs, and it achieves permutation invariance by using a symmetric max pooling function. The problem of this method is that it doesn't consider the local geometry in point clouds. To capture a wider context for each point and learn richer local structures, PointNet++ is proposed to hierarchically group points and progressively learn from larger local regions. Multi-scale and multi-resolution grouping are also proposed to overcome the problems caused by non-uniformity and varying density of point clouds. However, the farthest point sampling used in this method limits the scalability of this method. Further, point convolution methods are proposed to directly achieve convolution operation on unstructured point clouds. Point CNN is proposed to further explore the spatially local correlation. They propose an X-convolution operation to simultaneously weight and permute the features to canonical order. The problem of this method is that it failed to achieve permutation invariance. Later, The kernel point convolution is further proposed. The main idea of this paper is to map the raw point clouds to predefined kernel points, and then do convolution operation on these kernel points. To process large-scale point clouds. Superpoint graph is proposed to represent the point cloud as a set of interconnected primitives and superpoints. They first use geometrical partition and then build a superpoint graph, while PointNet is used to learn superpoint embedding, and GRU is responsible for message passing. FCPN utilize a hybrid representation of point clouds. This method takes the raw point clouds as input, and then use 3D convolutions internally. This method can process large-scale point clouds and has good scalability during inference. Although remarkable progress has been achieved in recent years, there are several limitations in existing methods. First, most approaches are limited to extremely small 3D point clouds, for example 1 meter by 1 meter blocks with 4K points. For example, PointNet has to split the whole room into several small blocks and then do segmentation on these individual blocks, which leads to inconsistent segmentation results since the network cannot perceive the whole geometry. As we can see, the table is misclassified as half table and half chair. Second, few methods such as SPG can directly process large-scale point clouds, but they either rely on time-consuming preprocessing or computationally expensive voxelization steps. Therefore, the research question is, can we develop a method that is able to process large-scale point clouds directly, without block partition and block merging? This can make sure the network can take the whole geometry into consideration. Second, the network should be computationally efficient and memory efficient, without time-consuming preprocessing or voxelization steps, so that it can inference a large-scale point cloud in a single pass. Finally, it should be also effective and accurate. It can compute the complex geometric structures and prominent features. To achieve this goal, we propose our RandLA-Net, an efficient and lightweight neural architecture to directly infer per point semantics for large-scale point clouds. The main idea of our network is shown in this figure. First, given a large-scale point cloud with millions of points spanning up to hundreds of meters, to process it with a deep neural network inevitably requires those points to be progressively and efficiently downsampled in each neural layer, without losing the useful point features. Therefore, we identify the key problems for efficient large-scale point cloud processing is, first, an efficient point sampling, second, an effective local feature aggregation operation. Since there is still no standard sampling strategy for large-scale point clouds. First, we analyze and list the pros and cons of existing sampling approaches. For heuristic sampling, farthest point sampling is the most widely used method in literature. It has good coverage, but has high computational complexity, which is quadratic to the number of points. For inverse density important sampling, it is able to control the density of point clouds, but sensitive to noise. Random sampling has superior computational efficiency and memory efficiency, but may discard useful features. For learning-based methods, generator-based sampling directly generates a task-specific subset to approximately represent the original large point set, but they need computationally expensive FPS matching. CRS use the reparameterization trick to achieve end-to-end training, but it requires a large weight matrix and leads to unaffordable memory cost. Policy gradient sampling (PGS) formulates the sampling operation as a Markov decision process, but it is difficult to converge due to the extremely large exploration space. To summarize, FPS, IDIS and GS are too computationally expensive, CRS approaches have an excessive memory footprint and PGS has extremely large exploration space. Therefore, random sampling is by far the most suitable approach to process large-scale point clouds. However, the new question is, random sampling may result in many useful point features being dropped. How to preserve these useful features? To this end, we propose a powerful local feature aggregation module to progressively increase the receptive field for each 3D point, so that the geometric details are more likely to be preserved. As shown in this figure, it mainly consists of 3 neural units: 1. Local spatial encoding, 2. Attentive pooling, and 3. Dilated residual block. Given a point cloud together with per point features, the local spatial encoding unit first find the neighboring points for each point by using KNN. Then, we explicitly encode the relative point position of all neighboring points, so that the corresponding point features are always aware of their relative spatial locations. This tends to aid the network to capture the local geometric patterns. Finally, the encoded relative point position features are concatenated with its corresponding point features. We then use attentive pooling module to aggregate the neighboring feature set. Instead of using max or mean pooling to hard integrate the neighboring features, where the majority of the information has been lost, we turn to the powerful attention mechanism to automatically learn important local features from the neighboring feature set. In particular, we first design a shared function g to learn a unique attention score for each feature. We then regard this attention score as a soft mask which automatically selects the important features. Since the large point clouds are going to be substantially downsampled, it is desirable to significantly increase the receptive field of each point, so that the geometric details of input point clouds are more likely to be reserved, even if some points are dropped. Therefore, we stack multiple local spatial encoding and attentive pooling units together with a skip connection as a dilated residual block. As shown in this figure, the red 3D point observes k neighboring points after the first aggregation operation, and then is able to receive information from up to k² neighboring points. This is a cheap way of dilating the receptive field and expanding the effective neighborhood through feature propagation. This is the architecture of our RandLA-Net. We stack multiple local feature aggregation modules and random sampling layers together, and we follow the widely used encoder-decoder architecture with skip connections. This network consists of 4 encoding and decoding layers, followed by 3 fully connected layers and a dropout layer to predict the final semantic labels. The downsampling ratio is set to 4 in each layer. For the experiment part, we first evaluate the efficiency, the sampling time and GPU memory consumption of existing sampling approaches by increasing the number of points from 1000 to 1 million. We can see that, for large-scale point clouds with million-scale points, both GS or FPS and IDIS are time-consuming, while continuous relaxation-based sampling are memory-costly and policy gradients-based sampling is difficult to converge. By contrast, random sampling has superior time and memory efficiency overall. Further, we evaluate the efficiency of our RandLA-Net. We show the total time, parameters and memory consumption of several methods on the validation set of SemanticKITTI. That is sequence 8, which has more than 4071 frames of large point clouds. We can see that our RandLA-Net takes the shortest time, translating to 23 frames per second, to process the whole sequences, which is 200x faster than SPG. We then show the results achieved by our RandLA-Net on several public benchmarks. For the Semantic3D, we use overall accuracy and mean IOU as the main evaluation metrics. We can see that our RandLA-Net achieves the state-of-the-art in this dataset. Then, for SemanticKITTI dataset, which consists of several litter point cloud sequences, our RandLA-Net also surpasses all point-based methods by a large margin and also has far fewer parameters than projection-based methods such as DarkNet 53. We finally report the 6-fold cross-validation results of our RandLA-Net on S3DIS indoor dataset, which consists of more than 200 indoor rooms belonging to 6 large areas. Our RandLA-Net also achieves on par or better performance than the state-of-the-art methods. We also show the results achieved by our RandLA-Net and other approaches in the Toronto 3D dataset. Note that only the 3D coordinates of each point are fed into the network for fair comparison. It can be seen that our RandLA-Net achieves the best results on this dataset in terms of MIOU, improving the previous state-of-the-art from 60.96% to 66.63%. We also noticed that road marking is the hardest to be recognized by all approaches. Primarily, this is because the pure geometric patterns of road marking cannot be easily distinguished against its neighborhood. Particularly, given only 3D coordinates of points, it is virtually impossible to differentiate the road marking and road. This motivates us to include the appearance of points to further improve the accuracy. We simply train our RandLA-Net with both 3D coordinates and color information as input. As shown in the last row of Table 5, the IOU score of road marking has been significantly improved by 27%, demonstrating the importance of appearance in this difficult case. We finally show the results achieved by our RandLA-Net on the NPM 3D benchmark. In this dataset, only the 3D coordinates of each point is available. Due to the relatively lower scores of 2 minority classes Trash Can and Pedestrian, our RandLANet achieves a mean IOU score of 78.1%, ranking after the latest LightCon Point and KPCon. Primarily, the point features of Trash Can and Pedestrian are very likely to be randomly dropped in our RandLANet because the two categories only have extremely small number of points. Here we show some qualitative results achieved by our RandLANet on S3DIS dataset. Different colors mean different semantic categories. We can see that our RandLANet achieves superior segmentation performance on large-scale point clouds. Then we show the qualitative results on the Semantic3D dataset. This is an outdoor dataset. We can see that the proposed RandLANet is able to achieve consistent segmentation performance. We finally show the qualitative results achieved by our RandLA-Net on SemanticKITTI dataset. This is the most challenging dataset as it has 19 semantic categories. Moreover, most of the point clouds are sparse and incomplete. However, our RandLANet can still achieve satisfactory results with real-time efficiency. We also conducted several groups of ablation studies. As shown in Table 5, the greatest impact is caused by the removal of the chain spatial embedding and attentive pooling blocks. We also investigate the effects of different spatial information in our framework. Finally, we further evaluate how the number of aggregation units in our dilated residual block impact the entire network. For detailed results and analysis, please refer to our manuscript. To summarize, the main contributions of this paper are as follows. We introduce a computationally and memory-efficient network for large-scale point cloud segmentation. Also, we analyze and compare existing sampling approaches, identifying random sampling as a suitable component for efficient learning on large-scale point clouds. Finally, extensive experiments on large-scale datasets have also demonstrated the high efficiency, scalability, and robustness of our approach. RandLANet is able to process 1 million points in a single pass with up to 200 times faster than existing approaches. Finally, we quickly go through our latest work, SENSAT Urban Dataset, which is an urban-scale photogrammetric point cloud dataset with nearly 3 billion richly annotated points. Unlike existing datasets for objects, rooms and roadways which are usually less than 200 meters in scale, the SENSAT urban point clouds continuously occupy kilometers in real-world urban areas, opening up new opportunities towards urban-scale applications such as smart cities, and large national infrastructure planning and management. Different from most existing dataset, the point clouds in our dataset are reconstructed from high-resolution aerial images. Here we show the survey of a region in Cambridge. All 9 flight plans, as shown in the left side, are collated together to cover the site. Lines with different colors represent different flight paths of UAVs. We also provide the data distribution and some examples of our SENSAT urban dataset. We also extensively evaluate the performance of state-of-the-art algorithms on our dataset and provide a comprehensive analysis of the results. In particular, we identify several key challenges towards urban-scale point cloud understanding. For the future work, we are planning to organize a competition in large-scale point cloud segmentation. Please feel free to join us if you are interested in our work. We firstly study how the large-scale urban point clouds can be pre-processed, to adapt to existing approaches without losing segmentation accuracy. The early PointNet and PointNet++ typically divide the point clouds into 1 meter by 1 meter blocks. This is however highly time-consuming for such a large input tile, and causes the object geometry to be fragmented across blocks. Since there is no standard and principled preparation steps in literature to partition the large-scale point clouds, here we organize the data preparation into 2 separate steps and then demonstrate the impact of different data partition schemes. From the results we can see that, first, both PointNet or RandLA-Net-based baselines achieve much higher scores when the input sets are density constant, compared with cases where the input sets have fixed volume. Second, using grid downsampling to reduce the raw 3D point clouds demonstrates marginally better results than random downsampling for both PointNet and RandLA-Net. One of the key differences between our SENSAT urban dataset and the existing litter-based is the availability of true RGB color for every 3D point. Intuitively, the colored point clouds tend to be more informative and can provide the networks with additional features for better segmentation accuracy. However, networks may overfit the appearance and fail to learn robust features from the geometry. Here, We experimentally explore the necessity of colorful appearance for better semantic learning of several key categories, highlighting the advantage of photogrammetric point clouds over litter-based point clouds. All of PointNet, PointNet++, KP-Con and RandLANet achieve significantly better segmentation accuracy when the networks are trained given both point coordinates and RGB information. Fundamentally, this is because a number of urban classes, for example, bridge, footpath, water, etc., are virtually impossible to be discriminated between, if only supplied with 3D coordinates. Fundamentally, urban areas are dominated by a small number of categories such as vegetation and road, while the minor yet important classes such as bike account for a minute portion of points. This extremely skewed distribution is another significant challenge arising from our SENSAT urban dataset. To alleviate this problem, a typical solution is to use more sophisticated loss functions. We evaluate the effectiveness of 5 off-the-shelf loss functions, with PointNet and RandLANet as baselines. From the results we can see that the inclusion of advanced loss functions indeed improves the segmentation performance. The MIOU scores gain up to 5%. Notably, for the extremely challenging category bike, the baseline RandLANet trained with weighted cross-entropy and square root weights obtains more than 20% improvement. This shows that data imbalance can be alleviated, to an extent, by using off-the-shelf loss functions. However, even this increased performance is hardly satisfactory, and we suggest that it is still an open question to explore more effective solutions to fully tackle this challenge. A common issue of deep neural networks lies in their inability to directly generalize to unseen scenarios. To this end, our SENSAT Urban includes large-scale point clouds from 2 different urban areas, which allows us to fully evaluate their generalization ability. We conduct experiments based on 5 baselines: PointNet, PointNet++, SP-Graph, KP-Con, and RandLANet. It can be seen that the segmentation performance of all baselines drops significantly when the trained models are directly applied to novel urban scenarios. The MIOU scores have up to 20% gaps for most approaches. Interestingly, the major categories such as ground and building do not observe severe performance drops, while the classes such as rail, street and water have the worst generalization scores. Due to a lack of realistic datasets, few studies have been conducted to investigate this critical issue of generalization. It is thus an open question of how to robustly label novel urban scale regions. Many thanks for your attention and time. Hope you are doing well and staying safe in this unusual time.